Control surface allow a pilot to adjust and control the aircraft flight attitude. Development of effective set of flight control surface was a critical advance in the development of aircraft. Early effort at fixed-wing aircraft design succeeded in generating sufficient lift to get the aircraft off the ground. But once aloft, the aircraft proved uncontrollable, often with disastrous results. The development of effective flight control is what allowed stable flight.
Primary flight control surface consists of aileron, elevator and rudder. And for the aileron, it is located hinge control on the trailing edge of the wing and near the wing tip. They are moved from the cockpit by the rotating the control wheel. They move differently. When the control rotated to the left aileron moves up and right aileron moves down. It is the longitudinal axis runs along the center of the fuselage from nose to the tail. Movement about this axis is called rolling. The next primary flight control surface is elevator. It is located the surface hinge to its trailing edge of the horizontal stabilizer, varies the tail load to control the pitch attitude of the aircraft. The elevator is connected to the control column. When the control column pulls, the elevator moves up and the aircraft move will be shut. Pushing the control column will force the elevator down and aircraft now will pitch down. It is the lateral axis run from the wing tip to wing tip. Movement about this axis is called pitching. The final primary flight control surface is rudder. It is located vertical control surface hinge to the aft of the vertical stabilizer and designed to apply yawing moments to the aircraft. The movement of the rudder is controlled by the rudder pedals operated by the feet of the pilot. When the right pedal is pressed, the rudder deflects to the right, thus bringing an increase of dynamic air pressure on its right side. This will make the aircraft nose yaw to the right. Its vertical axis passes vertically through the center of the aircraft. Movement about the axis is called yawing.
Secondary flight control surface consists of flaps, trim tabs, balance tab, anti-balance tab, servo tab, spoiler, slat, slot, and leading edge flap. Flap located at inboard trailing edge of wing. The function is to extend the chamber of the wing for greater lift and slower flight, and also to allow control at the low speed for short field takeoff and landing. Trim tab located at trailing edge of primary flight control surface. The function is to reduce the force needed to move a primary control surface. Balance tab located at trailing edge of primary flight control surface. The function is to reduce the force needed to move a primary control surface. Anti-balance tab located at trailing edge of primary flight control surface. The function is to increases field and effectiveness of primary control surface. Servo tab located at the trailing edge of primary flight control surface. The function is to assist or provide the force for moving a primary flight control. Spoiler located at the upper end or trailing edge of wing. The function is to decrease the lift, can augment aileron function. Slat located at the mid to outboard leading edge of the wing. The function is to extend the chamber of the wing for greater lift and slower flight, and also to allow control at the low speed for short field takeoff and landing. Slot, located at the outer leading edge of wing forward of aileron. The function is to direct air over upper surface of the wing during high angle of attack, and also to lower stall speed and provide control during slow flight. The last one is leading edge flap. Leading edge flap, located at inboard leading edge of wing. The function is to extend the camber of the wing for greater lift and slower flight, and also to allow control at the low speed for short takeoff and landing. Types of flaps. First, plain flap, located at trailing edge and inboard side of aileron. When it's lowered, both drag and the lift are increased. The second one is split flaps. The trailing edge of the wing is split and the bottom may be lowered. Increases both lift and drag. However, because of the limited effectiveness of both plain and split flap, both types are no longer in use on modern aircraft. The third one is a flower flap. Flower flap fit into the lower surface of the wings, where when they are extended, they slide outwards and downward on rails. Both camber and wing area are changed, allowing an appreciable increase in lift and a large increase in drag. The last one is a slotted flap. Slotted flap has a gap between the flap and the wing forces high pressure air from below the wings over the flap, helping the airflow remain attached to the flap, increasing lift compared to the split flap. Kruger flap. Kruger flap is the high lift device that are fitted to all or part of the leading edge of the wings of the some aircraft type. The aerodynamic effect of the Kruger flap is similar to that of slat. However, they are deployed differently. Kruger flaps are mounted on the bottom surface of the wings and are hinged at their leading edge. Actuator extend the flap down and forward from the undersurface of the wing, thus increasing the wing camber, which in turn increases lift.
There are 6 types of tabs, which is trim tab, controllable trim tab, balance tab, servo tab, anti-servo tab, and spring tab. The first tab is trim tab. In order to allow hands-off control and also to reduce fatigue of the crew, trim tab was introduced. Trim tab moves opposite direction of primary surface. To correct an aircraft nose down out of trim condition, the elevator tab is moved down, resulting in the elevator moving up. The next tab is controllable trim tab. A controllable trim tab is adjusted by the mechanical means from the cockpit, usually with an indication of its position being displayed to the pilot. Most aircraft have trim on the pitch control, and more aircraft have more trim on the 3 axles. Pilot control by the lever, wheel, switch, and others, by mechanical, electrical, or hydraulic actuation. Balance tab. A balance tab is linked to the aircraft in such a manner that a movement of the main control surface will give an opposite movement to the tab. Thus, the balance the tab will assist in moving the main control surface. Balance tabs are particularly useful in reducing the effort required to move the control surface of a large aircraft. Servo tabs. A servo tab is one of the directly operated by the primary controls of the aircraft. The control moves the tab, and the tab in turn develop forces which move the main control surface. The system is also used to reduce effort required to move the control on a large aircraft. Anti-servo tab. Stabilizers are very sensitive because of the great amount of surface ahead of the pivot point. To decrease the sensitivity, an anti-servo tab may be used. When the trailing edge of the stabilizer moves upward, the trailing edge of the anti-servo tab move up as well. This produces an aerodynamic load that attempts to pull the trailing edge down. Final tab is spring tab. The spring tabs, like some servo tabs, are usually found on large aircraft that require large force to move the surface. Purpose of the spring tab is to aid the movement of control surface. spring tabs are progressive in their operation so that there is a little assistance at slow speed but much assistance at high speed.
When ailerons are moved, the downgoing aileron tends to produce more drag than the upgoing one. If the downgoing aileron produces too much drag, then it may tend to turn the aircraft in the wrong direction. Method to counter adverse yaw. First is freeze the aileron, where the leading edge of the aileron is designed to protrude into the extreme when the aileron is raised, thus causing extra drag. Second is differential aileron. The downgoing aileron to move through a smaller angle than the upgoing aileron. This results in greater drag on the upgoing aileron.
Bob weights. Bob weights are sometimes known as counterweights. Their purpose is to change the amount of control force required to deflect the control column under different G loading. Normally, the amount of force the pilot must apply to the control column, assuming reversible controls, varies with speed only. However, by installing a bob weight, the aeronautical engineer can make it more difficult to pull on the control column as G-force increases. The purpose of the bob weight is to reduce the likelihood the pilot will overstress the aircraft.
Stall is a condition in aerodynamic and aviation wherein the angle of attack increases beyond a certain point such that the lift begins to decrease. Therefore, aircraft require a system to warn the pilot of an impending stall. There are several stall warning systems in use. First, pneumatic, second, electrical. Pneumatic system is common on light aircraft. In this system consists of plenum chamber and adjustable plate. Plenum chamber is mounted in the wing leading edge. Adjustable plate can be adjusted so that in normal flight altitude, a slot in the plate coincides with the stagnation point of the wing, act as part of the leading edge. The system works. The plenum chamber is connected by tube to a horn assembly in the cabin as the angle of attack is increased. The slot is so positioned that it reaches low pressure area sufficient to draw air through the horn assembly, which will emit a noise and alert the pilot to an impending stall. For electrical, this is typical of a system fit to larger aircraft. This is a simple system that employs first a micro switch, which is a transducer, and a vane. The transducer is mounted in the wing leading edge such that the operating vane is at the stagnation point during normal flight. The system works as the aircraft angle of attack increase. Operating vane effectively move up and away from the stagnation point until the one point it will overcome a spring pressure to deflect the vane and close the micro switch contact. This completes a circuit to eliminate a warning light and sun warning horn. This should occur just prior to reaching the stop.